Hi, welcome to another experiment for our 1212 lab here. We're going to be talking today about our molar mass experiment, kind of a new variation on it that we're kind of going and kind of trying out. So what we're going to be doing in this experiment, we're going to be talking about kind of what's called boiling point elevation. And to kind of be able to talk a little bit about boiling point elevation, we want to understand what it is, kind of why it works a little bit, and what's the main equation that we're actually going to be using to do any calculations for this experiment as well. And then we'll actually take a look at how that all ties into calculating the molar mass of something, and how we'll be doing that for urea in today's experiment. As a starting point though, boiling point elevation is what we call a colligative property. And so what it means for something to be a colligative property is simply that it's a property of solutions in particular that depends solely on how many particles are actually dissolved in that solution. So for instance, if you have, say, like a solvent that's just water, and you put an ionic compound like sodium chloride in it, that would be the actual properties of that aqueous solution with sodium chloride are going to depend on how many sodium chloride particles end up in that solution. And one of the unique things about colligative properties is they don't care about what the substance is that's dissolved in your solvent. It's really just about how many particles are there. And you'll see that kind of has some interesting impacts on things on whether the solute is a covalent molecule or an ionic compound, and whether the solution's aqueous or not, and kind of what effects that's going to have. We'll talk about that with the Van Hauf factor here in a moment. So colligative properties, big thing here, they depend solely on the amount of particles in the solution. So I'm going to say particles dissolved for right now. But that's the big thing, is however many particles are dissolved in solution, that's what's going to have the actual kind of large impact on the property itself. Now, in our case, the colligative property in particular we're looking at for this experiment is boiling point elevation. And it's the phenomenon that as you add more and more particles to your solution, the boiling point of the solution actually goes up. Now, a couple of reasons for that to kind of think about, kind of putting some things together, both I think from previous chapters back in chapter 11, up to another colligative property with vapor pressure that if you haven't talked about in lecture will probably be coming up shortly as well. And if we think about boiling in general, a liquid is always going to boil when your atmospheric pressure and the vapor pressure of that liquid are equal to each other. That's kind of what it means to be boiling in a sense. So for us, kind of when we're considering kind of what's going on and why adding things to our solution is going to impact the boiling point, the more and more particles we add to our solution, it's going to start getting harder for all the solvent molecules that are in that solution to actually escape, right? So if I just imagine like having a beaker with solution in it, and all these, the more other just random particles that are there, the solvent molecules are going to have attractive forces and collisions with those other particles. That's going to prevent the solvent molecules from escaping to the gas phase to create that vapor pressure and actually kind of reach that state where you're boiling, right? So the more stuff in our solution, really the kind of net effect is that our vapor pressure of the liquid goes down, but things don't boil until vapor pressure hits our actual atmospheric pressure. So the way we counteract that is in order to get our solution to boil with all the extra kind of junk inside of it, then we have to raise the temperature higher to be able to get that solution to actually boil. And so the net effect is boiling point increases with the more kind of particles or other things besides the solvent that are actually dissolved in that solution. And again, the big thing impact here as far as like the colligative property side, it doesn't matter what that compound is that's dissolved, it's just how many kind of free-floating particles are in there. They're going to cause some of those collisions and attractive forces and kind of prevent your solution or your solvent molecules in particular from being able to get to the vapor phase. Now, calculation-wise, the major equation of this kind of effect when we talk about boiling point elevation is this one. So I will talk about kind of each of the pieces here individually in just a second, but basically we have our change in boiling point. Should always be a positive number because the boiling point's going up as we add things to our solution. I here is something called the Van Hauf factor. So this thing right here, our Van Hauf factor, is really a measure of how many particles does your solute break apart into in the solution. And so to give an example of this, let's say you take sodium chloride, and let me switch my markers here, hopefully something's not dying, apologize. So if I have sodium chloride and I put this in, say, water, sodium chlorides should be breaking apart into sodium ions and chloride ions. And since it's making 2 particles for every kind of 1 sodium chloride that I have, our I that we would put over here would be 2. It's kind of a measure of how many particles is your solute breaking apart into. So this really only matters for ionic solutes being put into water, so that those ionic compounds are breaking apart. And in a perfect world, sodium chloride probably almost completely dissociating, so it's been Hauf Factor. We typically for calculations will treat it as 2. In reality, it's usually slightly less than that because there will be some kind of sodium chlorides that actually don't break apart, kind of a very small percentage of them. So in reality, it might be like 1.8 or 1.9 if we were to do calculate I experimentally. But for a lot of calculations, we just kind of assume total dissociation. Now, for our experiment today, we actually don't have to worry about that for the most part, because our I for what we're going to be looking at today is actually just going to be 1, because we're not using water as a solvent, and we're using a covalent molecule actually as our solute. We're using urea. And so urea is just a covalent molecule. Putting it, and we can even put it in water, but water or ethanol, which is what we're using as our solvent, it's not going to break apart. So since the solute molecule won't break apart, the Van Hauf factor is just 1 in that case. So for what we do today, I is just going to be 1. This Kb in this equation is really just a constant that's related to how much the boiling point is going to change based on what your concentration and molality is. And so the bigger your Kb constant is, the bigger boiling point change you're going to get with a smaller number of particles in the solution. One of the reasons we're not using water as our solvent today is water's Kb value is actually really tiny, so we would have to add a lot of particles to a aqueous solution to actually get the boiling point to change a noticeable amount. So hopefully for today's experiment, we're going to do this with ethanol, and we'll have a more noticeable boiling point change. It might still only be like 1 degree or 2 degrees kind of at the most, but that's a lot bigger change than what we'd have seen if we'd have tried to use water instead. Some organic solvents, you can add just a little bit of an organic molecule to it, and boiling point might change like 4 or 5 degrees. It's really kind of dependent on what the actual solvent is more than anything else. Again, the solute part doesn't really matter because this is a colligative property. All right, now the last part of this equation, this lowercase m, this is molality. So we'll highlight this here. This is not mass, this is molality. Right, so we're talking about moles of our solute per kilograms of the solvent, kind of unit-wise. And that will be important when we get to the very end of our calculation and we're trying to look at how do we find the molar mass of urea, which is kind of the last thing I'm going to show from kind of a conceptual side, and then I'll show kind of the experiment setup, kind of what things look like and what we're hopefully going to be looking for. So what we're doing for our experiment today, we're basically going to have an ethanol solution that we're going to find the boiling point of just plain ethanol. We're going to measure it, and then we're going to take a solution that has a specific amount of urea that we've dissolved in ethanol. We're going to go through and do the same thing. We're going to find a new boiling point so we can find the change. I think the lab gives us the actual Kb value for urea. I think it's like 1.22 degrees Celsius per mole, if I remember right. We just said it's going to be 1 because urea is a covalent molecule. It's not going to break apart, which means from the data that we collect or are given to start, we can solve for the molality. So our goal is we're going to solve for the molality from a calculation standpoint. And once we have that, we actually want to approximate the molar mass of our urea. If you look at the actual solutions that have urea in it, they'll tell you that it's like 1.25 grams of urea per, I think, like 25 milliliters of ethanol. I apologize for the marker dying a little bit and kind of squeezing in the bottom of the board here. But this is the actual true concentration of that solution, but this is not what we're using for any of the calculations. We're going to use the molality that we kind of solve for out of this equation. And since that has units of moles per kilogram, if we know the kilograms of our solvent that we're using, we're going to give you the density of kind of our solution to kind of go with things for like the ethanol. If you know the volume of ethanol you measured out, we can approximate what is the actual mass of ethanol in grams and convert that to kilograms. And then if we know the kilograms of the ethanol, the solvent that we used, and the molality, we can now solve for how many moles of urea should be in our solution. And if we know it was 1.25 grams that were in that 25 milliliters that we started with, if we know the moles and we know the effective mass of urea that should have been in our solution as well, now we can calculate what our approximate molar mass for urea is. And hopefully we can get something that's pretty close to its actual molar mass, which is right around about 60 or so grams per mole. So that's kind of the background or kind of the theory of what we're going to be trying to do from a calculation sense in this lab. It might sound a little weird at first, but once you actually kind of see it, it's not too bad, and especially once you start doing kind of from the lecture side calculations with a lot of these colligative properties, finding molar mass is one of the most common calculation types that we usually see. So it is something that does come up pretty frequently. But I think that covers most of the conceptual side. So I'm going to kind of switch views here. We're going to take maybe kind of a quick 1 or 2 minutes to take a look at the experimental side of things and kind of what that looks like. All right, so this is just kind of a quick display setup with kind of what we're going to be working with for this particular experiment. Fairly straightforward, but there's kind of a couple things just to look out for. We do have a hot plate, basically we just made a hot water bath here. Got the water hot so that we can take our ethanol solution, kind of put down in that solution and actually warm it up. Then we just have a lab quest with a thermocouple so we can measure the temperature of our solution as we go. And what we're going to be looking for is 2 things. So we're going to be looking visually for when the solution inside the test tube starts to boil. And I'll go ahead and just lower this now so you can kind of start to see this temperature rise while we kind of go here. And we're going to be visually looking at that, but we're also going to be paying attention to our lab quest and the measurements that it's recording, because it's telling us the temperature here, but you can actually have it just record the temperature over time. And so we'll actually see this. It's going to start increasing here on the screen as we go, and I'll show this screen in a minute as that temperature kind of continues to go up. But our temperature is going to kind of keep ramping, but at some point it's actually going to stop and plateau. Right, this is the one thing I didn't show visually previously when we were kind of going over some kind of conceptual ideas for the experiment. But as we measure our temperature of our solution, we're going to look for where is the plateau on our actual probe. You can actually see this starting to kind of slow down a little bit already. My temperature ramped up and now it's starting to flatten some. And if I look in the solution down here, it's going to start to probably bubble before too long. And we just want to look at when do we get bubbling that's going on inside of our actual test tube, and when do we see like a nice, very flat plateau for our heating curve from the lab quest. Those are kind of the 2 main things that we're looking for. And once it's very clear that our plateau is definitely flat and we've got some boiling going on in our test tube, we do not need to wait for this stuff to actually evaporate or boil out. In fact, I would say keep a very close eye on it as you start getting close to the boiling point, because once you've gotten very close to that boiling point, you really are going to want to probably take this out of your hot water bath so you can kind of just raise the clamp up so that the test tube comes out of the hot water bath, so that this stuff doesn't start to boil too vigorously and then actually shoot out kind of one of the extra empty holes up here in these stoppers. So if you're too careless, that's probably the one big safety hazard this lab could have, is if you heat this too much, don't pay attention, you can make kind of maybe a small ethanol, kind of like boiling ethanol, like jet stream coming out of the other hole that's open in that stopper. Probably have to have a decent amount of negligence for that to happen, but it's not impossible. So I do want people to kind of just be aware, pay attention. When you see kind of the plateau in our temperature, now you actually see it to go back down at this point because I took it out of the heat. But you should see a pretty steady rise in your temperature. And I would start recording on this pretty early. You can record it for up to 600 seconds. It shouldn't take 10 minutes for this kind of process to happen. If your test tube's kind of close to room temperature, as long as your hot water bath is boiling, it should heat up fairly quickly, and then you'll be able to actually see a very defined long kind of increase in temperature as the test tube contents heat. And then as it gets close to the boiling point, you'll see it start to slow and then level out and plateau. And we're interested in is what temperature is that plateau at. That's what we're going to use for the actual boiling point measurements that we'll then put into kind of the calculations that we described before. But that's the main bulk of kind of experimental setup pieces that we're really worried about. Like I said, biggest safety concern is really just be careful as you get close to the boiling point. If you're not careful and don't take it out of the heat soon enough, some of the ethanol can kind of start to boil at the top. So just do be careful. If that does start to happen, you can still likely just raise it from the clamp. Don't try to reach in and actually touch the test tube or anything like that itself, and it should be okay to be able to kind of go from there. But that should kind of cover most of the experimental setup. It's actually not too bad. Kind of once you get it set up and going, it's pretty easy to run kind of a couple quick trials for what we want to measure. And that's it for this week. So we'll see you all next time.